All right,
Okay.
what's
so,
my job?
So the situation is you're sitting, you, Mr. Brigart,
Okay.
sitting on a spinning office chair
Okay,
that is rolling down a hill.
it's spinning?
Yes.
Like, is it actually spinning, or is it just the kind of chair that could spin?
It's like rotating,
Okay,
like spinning.
so it is going around in
Yes.
circles,
and it's rolling down a hill at the same time.
alright,
And the hill has like a 30-degree angle.
alright,
And then we have more context for you.
okay. Okay, something like this, right? I'm in contact with the hill.
Yes.
Okay, alright,
Yeah, exactly. So you weigh in this scenario 115 kilograms.
115,
Mm-hmm. We thought it was a reasonable estimate. And the chair weighs 15 kilograms.
oh, okay, so, and I'm spinning with the chair, right?
Yeah, we're
Okay.
counting you basically as the
Okay,
same object.
so is it okay, will I need the separate masses? Can I just say 130 kilograms to keep things simple?
Yeah, but we kind of wanted you
Okay,
theory first.
yeah, right, I got, it's 115 me and 15 the chair,
Yeah.
okay?
So there are kind of two parts to the question. So
All right.
we'll start with the first.
Okay.
So assuming that you begin to feel nauseous at a rotational velocity of, why is this in radians? Okay, at a rotational velocity of 3 pi halves radians per second, and so, yeah, yes. Assuming you, at that rotational
Okay.
velocity, do we need an acceleration here too? Or just velocity?
I
Okay.
think we did pick it.
Assuming you began to feel nauseous at that rotational velocity, how many rotations did the chair take place? That's the question.
Okay,
How many times did the chair rotate?
so let me get
We need more info.
yeah, I need, okay, so let's talk about this, because if you have something that is spinning one direction, like this chair, spinning like this, right? And it's moving in another dimension, then those motions are independent. The rotation of the chair isn't gonna change as it goes down the hill. So, so it's gonna just go like this. And so what that means is, nothing about my motion here is gonna change the rate at which I'm spinning. So we need to have, so let me take a step back from this and point out, like, when I come up with labs for you or test questions for you, this is the process that I go through, because it is possible to set up a scenario and ask a question and have it like not quite go together. So in this case, I don't have any reason to think that there's any angular acceleration. If you don't give me any indication of angular acceleration,
Okay, we
then
do have that.
I'm gonna ask you, how fast am I spinning at the beginning? Because if it's greater than this, I'm already throwing up, and if it's not greater than this, then I'm never gonna throw up.
I think we said our angular acceleration is 1.4, is that what it's saying?
Okay, so it's 1.4
Radians.
radians per second squared, okay? And how fast am I spinning at the beginning? Because I can't possibly figure out how long it's gonna take to get to this angular velocity at this rate of acceleration unless I know how fast I'm going at the start.
Well, it can't be 0 because then we have to spin it.
Yeah, I think we were assuming it was going to start at velocity 0.
Okay, and so my initial, hang on, keep this color coded, 1.4 radians per second squared. My initial angular velocity is 0 radians per second. And the question is, how long will it take?
How many rotations of the chair to get to that?
To get to where? To get to here?
No,
you get
until you get nauseous.
Until I get
And
nauseous.
this is part,
Okay.
part A.
Yeah. So we have, and if it's, can I assume it's accelerating at a constant rate?
Yeah.
Okay, so I have an equation that looks like this. Final angular velocity squared equals initial angular velocity squared plus 2 times angular acceleration times angular displacement. We know this, we know this, we know this, I can find this. What does the ramp have to do with it?
That's part B.
Yeah.
Okay, that's part B. All right, so I think I can get part A with that, so I'm gonna make that many rotations. Okay, so now let's talk about part B. What's part B?
How far did you travel down the hill when you started to go north?
Oh, how far did I, yeah, so that's a kinematics problem. Yeah, so my initial angular velocity is 0. What's my final, or sorry, what's my initial linear velocity?
0.
Okay, so if my initial linear velocity is 0, so I think I see maybe where you were going with this. No, I do. I think, and so correct me if I'm wrong. You were picturing that there was going to be a connection between these angular variables and the linear variables. Is that right? Amy said yes.
That's what I was thinking.
Yeah, because otherwise, I mean, it's the same, like, basically, all I need, so this rotation is entirely independent of the linear motion. But I can find the time here. I've got enough information to find the amount of time that goes by. And I know what my acceleration is going to be here in a linear sense. My acceleration is going to be g times the sine of theta, and you told me that theta was 30 degrees. With time, initial velocity, and acceleration, you can find how fast I'm going at the bottom of the hill. But I think what you were thinking was something different, and what you were thinking is actually something that's a lot more interesting. You were thinking that there was going to be a connection between the rotational motion and the linear motion. What you were actually trying to ask about, and this is great because this is a terrific question to look at. You were really looking at this question. I'm not on a chair that's spinning horizontally. I'm in a hamster wheel. That's where I am, right? This is what you really wanted. You wanted me to be inside a hamster wheel. And that hamster wheel is rolling down the hill. So it's rolling the way I have it drawn. It's going to be spinning in the clockwise direction while it moves linearly down the hill. And if we assume that it rotates without slipping, because if it's slipping, then all bets are off, right? Like it could just be spinning in place and not moving at all. Or if it's moving linearly fast enough, it could be skidding, right? Like it could be rotating really slowly, but kind of dragging down. Like both of those are real scenarios that kind of they break apart our connection between our linear and our angular variables. But if we roll without slipping, then we've got some connection, right? Something about the rotation of this is going to match up with something about its linear motion.
Are we assuming in this situation that you're just solely like rolling down, or like that it's like spinning and rolling? Like if you had like a soccer ball and you were to spin it like in a direction, it would be like rotating but also going forward.
Yeah, we're assuming that it's not a ball, it's a wheel. So if it was a ball, you're right, it could be spinning on an axis that is not aligned with the axis of rotation that we're looking at here. But if it's a wheel, it's not going to do that. It's not going to spin like this as it goes down. It's going to roll, basically. That's what, I mean, rolling is spinning without slipping, right? That's kind of what it was. And there are a whole bunch of super interesting questions about this. One of which is, oh God, this is just an evil question. I love it. Let's say that there's like spokes in here, right? So you like, and the spokes have ladders on them. So it's like a wheel that's like this wide, and if I want, I can climb up the spokes. So my question to you is, where do I go to minimize the speed at the bottom of the ramp. That's a really tricky question that gets into a bunch of stuff that we didn't talk about, but it's kind of cool because you can picture it, can't you? You can picture, like, there is something about my location that's going to increase or decrease my spinning speed, isn't it? Want to see? Don't go anywhere. And remember, the camera is still rolling, so YouTube viewers, there's going to be some silence here. If you hear the students talking about me behind my back, I really appreciate you putting in the comments who it was so that I can punish them by giving them a bad grade later.
I wasn't far off, actually.
You guys kind of brought this on yourselves, by the way, because you're the ones who asked about nausea and me barfing, and so I think maybe now you're gonna get maybe a little of that. So let's see. Okay, so watch what happens when I hold my arms out, and can you see the difference in my rotation? Do you see that? Is that what, I don't have enough room, it's already on camera. I don't have enough room to hold my arms out all the way, and I can't, I guess I could hold, I could add a little bit of mass to this. I'm already feeling nauseated. It's gonna work out great. This'll help a little bit, and I'm probably gonna end up bonking into this, and now I don't have my arms, so I'm gonna get dizzy and fall over. I'll do this to myself. Okay, all right. See the difference? When I have these out, I'm moving a lot more slowly, right? So what's the deal with that? That has to do clearly with the location of the mass. I'm not changing any mass, right? Like, my mass plus the mass of these things is the same no matter what, and nothing is pushing or pulling on me, but somehow I'm speeding up and slowing down. That's kind of weird. So if you imagine me in a big hamster wheel, it was just the location of the mass that was changing, I'm gonna change the location of the mass here by climbing closer to the center or farther away from the center. How is that gonna affect the speed of rotation? What if I wanted to get down to the bottom of the hill as quickly as possible so that I could get out of this godforsaken hamster wheel? Or what if I wanted it to go slowly because the slower it goes, the slower I'm rotating and the less likely I am to get nauseated. Or am I? Right? Because there's another piece there, which is my location is going to influence my linear velocity, and maybe that's what matters, right? Like if you're in the very center of this thing, as it spins around really quickly, do you get as dizzy as if you're in the outer edge? Maybe. Like, what makes you dizzy? Is it your rotation, or is it the linear speed that's associated with that rotation? So all sorts of really good questions here. So, yeah, Griffin.
So I was gonna say, it's essentially like the fluids in your ears start to, spin quickly.
Yeah.
So if you were, for example, standing on the outside of a very large centrifuge,
Uh-huh.
it would just feel like it was heavier. Like you wouldn't even notice you were in a centrifuge unless you dropped something and noticed it was going really fast. Because it's not particularly the rotation itself, but the fluids in your ears. So when you're really close to the center of rotation, that's what causes it.
That's worse? I don't know. I think that's a reasonable hypothesis, and I don't know what the answer is. I think you could make the argument that being on the outer edge, you're gonna get dizzier more quickly.
Yeah.
Because you're moving really fast.
Well, you're covering more
Yeah.
distance, aren't you?
Yeah. What's that?
Like you're covering, you as a
You
person
are,
covering
yes,
more distance.
the linear distance is larger. The farther out toward the edge of the wheel you are, the farther you're moving in a linear path. And I think what accounts for dizziness and nausea and stuff like that is inner ear stuff, but it's also there's an optical piece too. So that's why, like, when you're on a boat or something, they say look at the horizon, you know, because it can get it's the disconnect between what your ears are telling you and what your eyes are telling you that can sometimes influence it. So I don't know the answer, but I'm not arguing with you, but it's an interesting topic. I mean, you could be right, but I don't know for sure. Okay, so let's think about this for a little bit. So if we think about the fact that my motion in here is going to be sort of like when I was moving those bars back and forth, and the mass of this whole system isn't changing, but I can speed up its rotation by like doing something with the location of that mass, then that leads to another question, one that would be a lot less likely to make anybody sick, and that is, what if I were to take 2 cans, like a can of beans and a can of soup, and let's say they have the exact same mass, and we're going to roll them down, starting from rest, a ramp that's the exact same length at the exact same angle. They have the same mass, same diameter, same size, same mass, same diameter. When do they get, which one gets to the bottom first?
So I think it comes down to rotational inertia.
Uh-huh.
Because, well, the closer, if the weight, for example, like if it's a ring,
Uh-huh.
where all the mass is on the outside, the rotational inertia, wait, let me think real quick because it's rotational inertia of the ring versus like a solid disc is, I think, wait, oh my god. Yeah, ring. Because the mass is like further from the center, so it has a greater rotational inertia, which means I think it hits the bottom slow later than the disc. I could be wrong.
You ready to put some money on that?
I could have thought of
Because
that.
I happen to have a can of soup and a can of beans, and if anybody's hungry, these expired 10 years ago.
Why do you just have these?
Huh?
Why do you just have
Physics
these?
purposes.
I mean, come on. Really?
Why don't we have you test out the hamster wheel thing? and make
This
it-
one expired so long ago that it didn't even, this was back before they even had expiration dates.
We're adding to the problem, you have to eat those and then you go on the hamster wheel.
Oh wait,
Yeah.
the disc.
The nausea, the rotational speed for nausea has just dropped considerably.
The disc hits the bottom first, then the disc hits the bottom because it has a lower rotational inertia. I said it wrong.
No, you said it right. You said,
Why?
you said the hoop will hit later.
Okay.
It has more inertia.
Yeah,
It's the
sorry.
same. It's the
I think,
same.
yeah, that's what I.
So what about these though? Which has more rotational inertia, a can of soup or a can of beans? They have the same diameter and the same mass, and the mass is distributed the same way.
It's not the same.
They're not, they're close though.
Which one's heavier?
They're about the same,
Okay.
about the same.
What ingredients does the soup have in it?
Oh, come
These
now.
are important questions.
Autolyzed yeast extract. It's just, no,
If like what?
it's broth. It's just chicken broth.
I'm gonna guess.
Chicken broth?
The bean go to the outside of the.
Nope.
Does
Nope, the beans these are refried beans. They're not going anywhere.
it mean that because they're expired, have they biodegraded some?
But imagine when it's rolling and it goes outside.
No, they won't. A little bit of air in the top will go
What
to
kind of
the
soup,
middle.
is it frozen?
Nope.
What if it's frozen?
Oh gosh, you guys, what a great question. Amy says, what if it's frozen soup? What do you think? Would that change anything, Caleb?
I would think so. I was going to ask, does the redistribution of mass matter? Because with the beans, like, given that they're refried beans, they're not going to change as much in how they're distributed as they roll. But with
Yeah.
the soup, it's more likely to fall towards the relative bottom of the
Not really though. I mean, the density of the liquid is pretty much uniform and stays uniform, even as it rotates.
Evenly
Yeah,
distributed.
Griffin?
If you have like a soup can, or maybe it's not a soup can, but like a water bottle that's full,
Yeah.
and you roll it down a hill, it oftentimes, I don't know, it seems like it takes time to accelerate the liquid on the inside, like to actually get that spinning. I don't know, I've kind of noticed that.
Oh,
Maybe
yeah.
that has something to do
So
with-
what he's saying is that if you have a can, if we were to look at a side view of a can, and just to make it as like clear as possible what's going on, if there's liquid in the can, then if this can starts to rotate, if this can starts to spin, it's gonna spin, but the liquid won't, at least for a little bit. And that's actually exactly right, and who's car people? You know, how does an automatic transmission work? Are you,
Yes.
Yeah.
can explain that.
okay, but it's a fluid dynamics thing, right? You have one thing that's spinning, that causes a fluid to start to spin, and as that spins faster and faster, that causes something else to spin.
Yeah.
And it has to do with exactly what we were just talking about, which is that if you spin this can, the fluid inside won't spin right away. It takes a little bit of time. The fluid on the outside starts to spin first. Why? There's friction. If we think about the fluid as being in layers, the layer closest to the outside of the can is gonna start to move, and then the layer next to that, and then the layer next to that. If you were to look at the velocity of these like layers of fluid, what you would see is the rotation is smallest on the inside and largest on the outside. And over time, eventually, it'll sort of all catch up, right? But initially, what you're likely to see here is very little of the fluid rotating. So Amy's question, does it matter if the soup is frozen? Yeah, it does. If the soup is frozen, they both end up at the same point at roughly the same time. It's only when the soup is liquid that that won't be the case. And why not? You're right, it's like something about, and it's something about moment of inertia, but what is that, like, what does that have to do with anything?
Wait, so that soup has been sloshing around in there for like over a decade?
Probably, yeah?
It might have chunks in it by now.
As the soup, as the can rotates, it's going to start displacing more and more of the soup inside.
That's-
And therefore, that's going to change the moment of inertia because
It
the
is.
distribution.
It is, it's gonna have a variable moment of inertia because of that, but my question is, why does that matter at all? You got the same amount of mass, it's moving down, it's being pulled by the same force. Why would whether the insides are rotating or not make any difference, right? Like with the can of beans, it's gonna rotate like this. What difference does that make? That's a nice, perfect circle, isn't it? Good work. Right, what difference does that make? Why does that make any difference?
Well, I guess inertia is kind of like something's resistance to change.
Yeah,
So if you have, part of that mass not resisting the change, then presumably it'll change quicker.
what will change quicker?
The speed, right?
Okay, and so your hypothesis then would be that the one with a lower moment of inertia is gonna have the fastest speed at the bottom of the ramp, or, which means it would get to the bottom the quickest.
Okay, really dumb question, but can you define moment of inertia in simple terms, like in this context? It's like,
Not exactly, but we could, I think, reasonably say that the can of beans, with the way that this is shaped with real thin piece of metal, we can just say it's uniform density. So yeah, the moment of inertia of the can of beans would be 1/2 mr squared.
oh, no, I
Okay.
mean more like conceptually, because I get it mathematically.
It's how hard it is to speed something up or slow it down rotation.
Oh, okay. thank you.
So I guess the question would be like, if I wanna spin these, which one is easier to get spinning faster? Or which one would be easier to stop? Like, that's what moment of inertia is meant. Yeah.
I just have a hypothesis. So you said if the beans don't move, that means, okay, well. if
The
liquid-
beans don't move relative to the outside of the
And the
can.
liquid does?
Yeah.
Okay.
The
Then-
liquid is essentially gonna maintain its position with respect to the ground
So
over the course of rolling down a short ramp.
then, isn't that gravitational potential energy is, some of it's being converted into rotating the liquid, whereas with the solid, it's not, so it's all going into kinetic energy, making it faster.
Other way.
Wait,
Yeah, if the liquid isn't rotating, so there's no kinetic energy, yes.
Okay.
So Richard's onto it, it has to do with energy. And basically what happens is, we know we start with a certain amount of gravitational potential energy. It's the same amount of gravitational potential energy in both cases. The final energy, assuming we're not losing stuff due to friction and all sorts of other stuff, is gonna be the same as well. Which one is gonna have more rotational kinetic energy? The one that has more mass that's rotating. The can of beans is gonna have a higher rotational kinetic energy, which means it will have a lower translational kinetic energy. So yeah, the can of soup's gonna go faster. So where do I go? Well, if I wanna go faster, go up to the center. If I wanna go slower, I go out to the outside. All right. We've got extension, and anybody who wants to keep talking about stuff can. I'm gonna shut the recorder off now though, and I'm gonna post this to YouTube, because why not? And your job then is gonna be to like be ready to do this kind of stuff on Friday.